We've seen that Riemann sums can be used to approximate the area under the graph of f of x over the interval from a to b. And now we've defined our definite integral as the limit as we send the number of rectangles to infinity of exactly such a sum. So it turns out that one way to interpret the definite integral from a to b of f of x is as the area underneath that curve over that same interval. What this means is that in certain instances, we'll be able to use geometry in order to evaluate a definite integral. To start with, I want to look back at the exact same two examples we saw in our last video. So we want to use geometry to evaluate, and we'll go through both cases. So the first one we looked at was the integral from 3 to 8 of the constant function 2. And in the last video, we went through how to evaluate that using the definition directly. To use geometry, what I need to make sure I can see is the graph of this function over the desired interval. So here would be my function f of x equals 2. And let's look at the interval from 3 to 8. Then the area we're looking at would be the area underneath this function over the interval from 3 to 8. So that means that in evaluating this integral, I can say that it is equivalent to that shaded area. That's the area of a rectangle with side lengths of 2, and the other one, 8 minus 3 is 5, so we would get 10. You'll note that's the exact same answer we got when we went through the definition, and of course we arrived there much quicker using this. The other example we've already seen in using the definition directly was finding the integral from 1 to 2 of the function 2 minus x. So again, let's approach this in a different way using geometry. To start with, we want to consider what that graph of that function would look like. So we're just, this was actually from 1 to 4, and I want to keep the same bounds we saw before. So let me fix that. 1 to 4. Okay, so put my y-axis here, and we can think about drawing this line 1, 2, 3, and 4. So for this function, leave myself some space. We know it's going to cross the x-axis at 2. When we plug in 1, we should get positive 1, and we should get negative 2. So this is my function. And to be a little bit more precise, when I talk about the area under the curve, what I should say is the area between the curve and the x-axis. So this crosses over the x-axis. And if I talk about the area, what I'm really looking at is two different shapes in some sense. So we have this blue triangle and we have a red triangle. So one thing that's worth noting here is that if you were to actually take this sheet of paper and measure with a ruler the area, you would treat everything as positive. Whenever we talk about area in context, we think positively. The distinction here is that when we're talking about definite integrals, all of a sudden it's possible to have negative area. So in particular, we would treat any area that lies beneath the x-axis as negative. That's because if you think about our definition, the height of our rectangles would be negative. In this picture, the blue area is positive as it lies above the x-axis. So what that means in terms of me evaluating this using geometry is we're going to take the area of the blue triangle and we're going to subtract the area of the red triangle. So with that process in mind, switching back to the black pen, the blue triangle, 1/2 base times height, both base and height are 1, and we're subtracting the area of the red triangle, both base and height are 2. That leaves us with 1/2 minus 2, or -3/2. And once again, that's exactly what we got from the definition. So the advantage here in using geometry is, of course, that this is a much quicker way to get to the end result. But the disadvantage is that we're not going to be able to look at every area of interest and recognize a familiar geometric shape. And I'll do one last example where using geometry is particularly useful. If you're asked to evaluate the integral, say, of square root of x from -2 to 1. So we can use geometry for this. Think about what this picture would look like. So the absolute value function for positive values of x is going to look like y equals x. And for negative values of x, it's going to look like y equals minus x. So this is the graph here. We're interested in looking at the area from -2 to +1. Notice in this example that both regions are going to be counted as positive because they lie above the x-axis. So we are interested in adding the area of these two triangles. So I can say that this is equal to 1/2 base times height for that triangle on the left, plus 1/2 base times height for the triangle on the right, giving me 2 plus 1/2, or 5/2. And I want to point out something that we can observe here. A common mistake, so I'll point out this is not equal to the absolute value of the integral. So this means that if you were to first use geometry to find this integral and then take the absolute value of your answer, you should find that you don't get 5/2, because the circled integral, you could imagine taking this picture and bringing that left-hand side down. So what would happen is we would have a -2 plus our 1/2. So we would end up with -3/2, and then the absolute value of that is 3/2. So in general, we have to be careful if we're asked to do something to the inside to our integrand. We don't want to assume that that's the same as doing the same thing to the entire integral.